Welcome everyone, I am Alexandre Mercier-Aubin, a grad student from the Université Laval in Quebec. I've written this paper with Jonathan Gaudreau and Claude-Guy Quimper, so let's get into it. So we have an industrial partner in the textile industry that funded our project. They proposed a scheduling problem, and we developed a mathematical model which we coupled with a search heuristic based on the traveling salesman problem. So our problem is to schedule non-preemptive tasks on looms. The tasks are pieces of textiles to weave. There are sequence-dependent setup times to get a loom ready for its next task. Each loom is a disjunctive resource. A loom can only weave one piece of fabric at a time. There are cumulative resources, which are the different employees working on the setups. The pool of workers is different for every setup type. But what are the setup types? There are major and minor setups. The major setups configure a loom so it can weave different types of textiles. There is at most one major setup per horizon of 2 weeks, so we decided to use an horizon of 2 weeks. The planification team usually create their schedule for only a week. We also present a list of the different number of employees of every profession. On a minor setup, the following profession will interact with the loom in a fixed order. Some profession might not always be needed. So there will be a weaver, beam tire, and finally the mechanics. Pieces of textiles are compatible with a set of loom configuration. We already know which task will be executed on which loom. The tasks are scheduled either before or after the major setup according to their compatibility. Pieces of textiles have a style which includes the thread type, color, weaving pattern, and much more. Two tasks with the same style are basically the same. For example, if you have three tasks, A, B, and C, and the task A has the same style as the task B, then the setup time from A to C and B to C will be the exact same duration. In our problem, we have many pieces of textile to weave. In our instances, it ranges between 571 and 841. Here is a simple example of a schedule with two looms. In this example, there is one employee of each profession. Each timeline represents a loom. Each rectangle represents a setup or a task during the timeline. If we look at the beginning of this timeline, we see that there's two mechanics overlapping on the different looms. Since there's not enough employees to do both tasks at the same time, we have to delay the second task. The same thing happens for bigger problems when we run out of resources. Since our model is pretty big, I split it in two. So let's go ahead and explain what's going on here. Bubbles will explain letters. The first equation shows our objective function, which is to minimize the weighted tardiness. It is essentially the sum of lateness weighted by task priority. Since there's at most one major setup per horizon of 2 weeks, and that we're scheduled for an horizon of 2 weeks, then it means that we can part every task by whether they're compatible with the initial configuration or not. Then we must model the disjunctive resources. Equation 4 says that a minor setup can start before the end of its task, while equation 5 encodes the fixed profession order. In this equation, T is a matrix that encodes setup durations, and N is the next job array. Equation 6 states that as soon as the minor setup is done, the loom must start weaving. To model the next job array, we use the circuit constraint on line 9. So let's say that we have a task I. The value at the position I and N will be the next job of I. In order to model the looms individually in the next job array, we use sentinel job. Those tasks are at the end of every loom, and they point to the first job of another loom. Equation 7 and 8 allow us to force the loom order for the sentinel jobs. Then equation 10 and 11 are cumulative constraints to model the worker pools. 10 is for the minor setups, while 11 is for the major setups. The final equation allows us to create a symmetry break for jobs with the same style. Two jobs with the same style and due date can be ordered by ID. This is due to the fact that they have the exact same transition matrix. Since we use the traveling salesperson problem to define our search heuristic, why don't we take a bit of time to explain what it is exactly? So there's a traveling salesperson that goes from city to city in order to sell his products. At the end of the day, the salesperson wants to go back home in order to rest. So he's willing to find the shortest circuit that goes through all the cities that he wants to visit. In other words, he wants to find the shortest Hamiltonian cycle that goes through all the cities. But you're probably wondering, how does it relate to scheduling? So let's say that we have a simple TSP problem with 4 cities, A, B, C, and D. The edges represent distances between every city. The shortest Hamiltonian cycle is in blue. To convert it into a scheduling problem, we can add a dummy node. This dummy node represents the start of a schedule. It is conveniently named node 0 since all of its edges are of weight 0. Instead of the node being cities, they represent tasks to schedule, and the edges are setup times between each job. So basically we end up with a solution to a scheduling problem without considering, let's say, cumulative resources and such. But it can be a good start for an initial solution or an initial value for the variables affected by the circuit constraint. So we can use it to create a proper schedule by introducing the cumulative constraint manually, and we can also use it to just extract the circuit that we can use as a search heuristic later on. So as I said earlier, we have 4 different datasets with an increasingly high number of tasks. We wanted to see how our algorithm would scale with different numbers of tasks, so we ended up cutting our dataset into smaller pieces. So from the different datasets, we sampled randomly different tasks. The first cut being 10% of its original size, then the second being 20, and so on, until we reach 100%. This way, we could compare the different methods on increasingly difficult problems. So we tested 2 basic heuristics. The circuit method uses a TSP solver to produce a circuit that will be used to generate a solution. Greedy, however, simply sorts tasks by due date. Both of those are heuristics, so they won't give the optimal solution, but they're quick to compute. To fairly compare the basic heuristic without solver to CP solver, we introduced the random circuit, which will be used as a branching heuristic to set the values of the n array. Compared to heuristics, search heuristics explore the whole tree. Therefore, it will eventually find the best solution. We can also extract the circuits of both heuristics and use them as branching heuristics. We've also validated if the large neighborhood search would improve solutions for our search heuristics. Every method is given a timeout of 15 minutes. This is how we compare the different methods explained in the previous slide. In this figure, the x-axis shows the number of tasks for each instance. On the y-axis, we see the weighted tardiness. We group the different dots by the method used. The 3 methods compared are circuit, greedy, and CP plus random. Every solution of every instance is represented by a dot in this figure. The colors of the dots change from green to blue according to how fast they were found. So here we basically compare 2 heuristics to a CP solver. Here we see that the circuit heuristic finds similar solution to CP plus random, while CP plus random continues to find better solutions over time. We also see that circuit is quick to compute. But what would happen if we decided to merge both? In this figure, both axes remains the same, while we used different groups and methods. Here, every method uses constraint programming since it was the best approach of last figure. We also use different search heuristics such as greedy and CP to initialize or end circuit. On the y-axis, we show results produced with the LNS or not. By analyzing this figure, we can see that the CP plus circuit is the clear winner. This is due to the fact that it actually finds better solution than CP plus greedy, and if you look well, CP plus random doesn't even find solution for all the instances. For some reason, the LNS seemed to work better with CP plus greedy and CP plus circuit. My guess is that since we've got a good initial circuit, it's easier to fix a few tasks than trying to correct a poorly made initial circuit. So overall, the best approach for a problem is CP plus circuit plus LNS. It is more stable since it found solution to all of our instances. It offers better performance by finding better objective value for the different instances. The solutions with this search heuristics are usually found faster than with others. Therefore, we can say that it solves our industrial partners problem. To conclude, we can say that we've designed a new TSP-based search heuristic. This search heuristic offers good solutions for our problem, and the solutions are found in reasonable computation time. Best of all, this algorithm has been implemented in the system of our industrial partner, and this alone could motivate our contribution. So thank you all for listening, and I'll leave you with a couple of references.